I'm Tahmid Soed Abtahi. I'm a grad student in University of Maryland, Baltimore County. And I've been working with Dr. Tinosh Mohsin in EHPC lab. I'm going to talk about my research, which is accelerating convolution neural network with FFT on tiny cores. The agenda for today is to go over the motivation and some contribution. I will give a small review of the backgrounds and the algorithms. I'll go briefly talk about Penn's many-core platform, which is developed by our lab. And then I'm going to show implementation results and their analysis. So what's the motivation behind this work? The amount of IoT device with detection capacity is increasing. And for detection, we need inference of high complexity algorithms, such as convolutional neural networks, which is right now top of the line. And it outperforms all its previous state-of-the-art solutions. And it doesn't need any data pre-processing or domain knowledge. However, if we want to transfer data to cloud, do the inference there, send back our result, it will take additional power, it will incur delay, and sometimes it might pose the risk of privacy. For example, let's say in driverless car, we need very fast real-time onboard processing. Now the problem is onboard embedded processors has limitation in computation and memory. Therefore, it is challenging to deploy CNN. So here I'm showing AlexNet, which is a popular object detection network. I'm showing the computation breakdown for different layers. The blue color shows convolution layers, and the yellow color shows rest of the layers, which are batch normalization, max pooling, fully connected layers. And from here we can see most of the computation is dominated by convolution layer. But convolution is computationally intensive, and also the memory transfer cost is high, since one memory location needs to be accessed multiple times. Therefore, if we want to use traditional CNN in embedded settings, it poses a problem. We are proposing FFT-based convolution for embedded CNN. I'll be showing computation and memory analysis for different object detection networks. I'm going to show energy efficient implementation for 3 different methods of convolution on 3 platforms: ARM A53 CPU, Penn's many-core architecture, and NVIDIA TX1 GPU. And then I'm going to show cross-platform and within-platform efficiency evaluation. So right now, what's the traditional convolution method used? It can be better explained by this diagram, where a 5x5 image showed in green is getting convolved by a 3x3 filter showed in yellow. We can see the filter is sliding across the image, and at each position it is doing a dot product with the patch of the image and with the filter, and we are getting the convolved features. The problem here, the amount of computation is very high, to the order of n square k square, n being the size of the image and k being the dimension of the filter. Also another problem is we need multiple memory access. Now we know that convolution in time domain can be represented by multiplication in frequency domain. So we are just using that idea to our advantage. We're doing fast Fourier transform on the image and the filter, doing a point-wise multiplication, and doing an inverse FFT of that to get the convolved feature. The advantage is we are reducing complexity to the order of n square log n. And the problem here is, if you see, after FFT, the filter size is getting higher to the size of the image. This means in this intermediate stage, we need additional memory. And if we have an embedded device which has shortage in memory, this is going to pose a big problem. Also, this needs higher point FFT, which requires more computation. The next approach is to use FFT overlap and add, where the image is segmented into blocks. The blocks undergoes FFT, we do point-wise multiplication with the filter FFT, and we do inverse FFT on the blocks. The blocks are then aligned and added to get the convolved feature. So this further reduces the complexity, and if you see, the filter after FFT operation is not getting to a higher size. This means the intermediate memory buildup problem is no longer there. A slight disadvantage is that we need additional logic for the overlap and adding mechanism. Now I'm going to talk about what network should I choose to deploy in my embedded device. The criteria should be, we need to have higher accuracy, and the amount of memory needed should be low. So I'm showing some popular object detection networks here. The trend is now we are going for a higher amount of convolution layers, but single layer of fully connected. We see that this is ResNet 20, which has 19 layers of convolution and 1 layer of fully connected. This needs a memory of 0.27 million, wherever its previous predecessors like AlexNet has 5 convolution layers and 3 fully connected layers, and the number of parameters it needs is 2.3 million, which is almost 10 times bigger than ResNet 20. The error rate here is 8.75, which is much lower than AlexNet and almost closer to human accuracy. Therefore, for our case, we'll deploy ResNet 20 train.cipher 10 network. Below, I'm showing a visualization of ResNet 20 and AlexNet. ResNet 20 has 19 convolution layers, as we talked before, and 1 fully connected layer at the end for classification. AlexNet has 5 convolution layers and 3 fully connected layers at the end. I'm showing a computation and memory access analysis on these 2 networks for 3 different sorts of convolution. In terms of operation count, we can see the black bar, which is showing FFT OVA convolution, is giving the lowest amount of operation count. In terms of memory access, direct convolution or the traditional convolution has the most amount of memory access because one memory needs to be accessed multiple times. In terms of parameter or the number of storage you need, FFT convolution requires the highest amount of memory storage since it runs into intermediate memory build-up problem, which you already talked before. I'm going to briefly talk about PEN's many-core architecture. It is power-efficient nano cluster. This is developed by our lab in EEHPC, and this has been presented in ISCAS and JLS-VLSI, and all the details can be found there. I will briefly go over here. We have 64 clusters connected by a hierarchy of routers, and each cluster has 3 cores connected through a low latency bus to a shared memory. This is fully placed and routed and synthesized in 65 nanometer technology. Each core can be programmed through custom assembly, and there is a 16-bit data path, and there is 197 cores, and the total chip area is 27 millimeter, and maximum power consumption is 12 watt. Here I'm showing how you want to, how we can configure our cores. So we write the code in custom assembly. There is a many-core compiler that creates the binaries, and we also preload the data, and the output is the binaries with which we can configure our cores to do specific task mapping. And these cores are also reconfigurable. So this is a high-level framework of what we are accomplishing here. So Intel Atom CPU is sitting outside as a host. It has access to input feature maps, which are the images, and each has access to the pre-trained models. That is, we train our models offline. Therefore, we have the binaries of the weights. Now it is streaming data into PENs. This means the input stream is going into different cores, and each core has access to different filters. So at one time, each core is getting the same data, and it is convolving with different filters at the same time. This means we are using task-level parallelism and taking advantage from it. The most amount of parallelism can be achieved when the number of cores is similar to the number of filters. And we also reduced crosstalk between cores by assigning each core to one filter. I'm going to show some results here. This is the most parallel implementation for PENs, and I'm showing 19 layers of convolution. The bars show different methods of convolution here. So one thing I want to point out is there are 3 different groups. If you look closely, this arises because of the fact in these groups, the number of output feature map is same, which is 32 by 32. Next group, it is 16 by 16. And the last group has 8 by 8. Also, the number of cores assigned to do the mapping is 16, 32, 64. for achieving the highest number of parallelism. One thing to look into here is the difference between direct convolution and FFT OVA conv in the first group is very visible. However, in the last groups where the ratio between the filter and the image becomes almost similar, the difference between the direct convolution and FFT-based convolution almost becomes less visible. Here I'm showing power mapping for 3 different types of mapping in pens. This is semi-parallel, this is most parallel, this is most parallel, this is serial, this is semi-parallel, this is most parallel. And we can see FFT conv has the highest number of power because it needs additional routers and memory for the intermediate memory that are created after FFT. Here I'm showing throughput for the different layers, and we can see FFT conv showed by the black bars have the highest amount of throughput in each layers. In terms of energy delay product, it has FFT conv showed by the black bar has the lowest energy delay product for 3 different types of implementation in pens. We also implemented the systems for ARM A53 CPU running on 1.2 gigahertz programmed with GNU Octave libraries. This is running on single core, and here I'm showing runtime for all the layers and for 3 different sorts of convolution. FFT OVA conv is 3.3x and 1.38 times more faster than direct convolution and FFT conv. We also did implementation on NVIDIA TX1 GPU for direct convolution, and I'm going to talk about comparison between platforms and within platforms. Within ARM, FFT OVA is 3.4 times faster than other methods. In pens, it is 2 to 3x times faster. Between platforms, ARM, pens, and NVIDIA, pens is almost 10,000 times faster than ARM and 3.3 times faster than NVIDIA TX1 GPU. In terms of energy efficiency, within platform ARM, FFT OVA is 3.3x times energy efficient. Pens is 2x times energy, inside pens, FFT OVA is 2x times energy efficient. Between platforms, pens is almost 9,000 times energy efficient than ARM and 17 times energy efficient than NVIDIA TX1 GPU. In terms of throughput per layer, within ARM, FFT OVA is 2.6x times better, and pens is 6 inside pens, FFT OVA is 6x times better. Between platform, pens is 7.5 times better than ARM and 6.9x times better than NVIDIA TX1 GPU. In conclusion, we introduced FFT-based convolution for embedded CNNs. We did computation and memory analysis for different object detection networks, and we did energy efficient implementation for 3 different sorts of convolution in 3 platforms, and we showed efficiency evaluation between and across the platforms. These are some of the selected publications from our group, and this concludes my talk. Thank you so much.